Good morning. In this lecture, we will discuss about DC motor. Since you are from the electronic side, most of the times you will be handling DC supplies also, maybe of a lower magnitudes. And in these DC applications, you may require motors which do operate on DC also. So that's fine. Today we will see the concept of DC motor, how it works, what are its important components, and where you can use these DC motors. In the last lecture, we have seen about single phase induction motors, why they are not self-starting and how can we self-start them. We have seen that they are widely used in domestic and commercial applications. And in today's class, we will go with this DC motor. We will see the important components, the construction orientation, and we will also see the operating principle along with the major applications of DC motors in electronics engineering. So I'll start with the working principle and then I'll move on to the components for this one. Okay. So as the name states, a DC motor, it operates on DC supply. It is a class of electrical motors. So far you have seen only AC motors, right? So DC motor basically converts this DC electrical energy into mechanical energy. In fact, any motor which is operated using DC is called as a DC motor, and it runs on DC power. It is also working on the simple principle. Its operating principle is also based upon simple Faraday's laws of electromagnetism. So it states that a current carrying conductor generates magnetic fields. When this is placed in an external magnetic field, it will encounter a force which is proportional to the current in the conductor and to the strength of the external magnetic fields. Simply, we call it as when a current carrying conductor, it develops a flux. When this flux is placed in greater flux, a magnetic field, then there will be a torque which is developed in the conductor. The same principle which we have seen in the last two classes of induction motors also. So it works on the current carrying conductor when placed in a magnetic field. It experiences a force which causes it to rotate with respect to its original position, which we call this one as torque. So a practical DC motor, it consists of the field windings to provide magnetic flux and also an armature so that it acts like a conductor to carry the currents. So two things, one is a field windings for providing magnetic flux and an armature which acts as a conductor for carrying of current. So when this armature interacts with the flux, then there will be a torque which will be produced. So the working principle, same. Electric current flows through a coil of flux, flows through a coil to develop a flux around the conductor. This is phi 1, and assume that phi 2 is already existing between the poles. So I'll take a conductor and I'm giving it a current, so automatically phi 1 is developed. Now I'll assume that there is already another flux which is phi 2. So when the two fluxes interact with each other, then automatically torque will be produced and this one will be moved. So, and the direction, as you know, it is given by Fleming's left hand rule. Okay. So what are the important parts now? If you see, this is my rotor. If you see, this is my rotor. We call it as an armature. We call it as an armature. And this stationary one, we call it as a stator, over which your poles will be there. So as already I have shown you, this is your rotor through which you be giving conductors. And this is your poles, right? And these poles are housed in a this is my simple construction. So these are the poles, north, south, north, south. Two pairs of poles are present here. And see, this is your pole core and this is your shoe. Shoe is a little bit just like a shoe type, so that it will be getting a enlarged space so that you can cover maximum periphery of this rotor. And over this you will be having field winding. These will be given some current so that it behaves as an electromagnet. So a field winding, pole core and pole shoe, and this entire one is called as a yoke, a mechanical supports. And here this internal one you call it as an armature, and over it you will be finding slots here, right? In this slots, your armature will be like this. I'm not a good at this, but yeah. So it will be like this. Slots will be there, and in these slots, your wire will be drawn, which will act as a conductor. You call these things as armature conductors. Okay. So at the center of this, you will be having a commutator to which all the conductors will be drawn, and they will be connected to this one. Okay. So if you see it in horizontal view, it will be like this. So it will be like this. Okay. So these slots you will be having conductors, and these will be joined at the center. You call this one as a commutator, and to this one there will be a shaft, and over the shaft you will be having brushes to collect the current from the armature conductors. Okay, this is the principle. Now we will see the important components of your DC motor. The first one is a yoke. We call it as a mechanical support to your entire machine. Okay, that is called as a frame of the DC machine, and it offers mechanical support which is intended for the ports. So it prevents your machine to stay enclosed in your yoke so that there is no moisture or dust or something doesn't fall into that one. So generally since it is used for mechanical support, we generally make it with the help of cast iron, which is very strong, or sometimes you can use this cast steel or rolled steel also. But generally we use cast iron, which provides a good mechanical support. And the next one is a pole and the pole core. Right, these are pole core. Okay, this is just like an electromagnet, which is a winding, just like a pole, which behaves as an electromagnet. When it will be having wire around it, when the current flows through it, then automatically it will act as a pole. So whenever the field winding is energized, then the pole will give magnetic flux, and it is mainly made up of a ferromagnetic material. We generally use iron or steel. Generally, to reduce the losses, we will be laminating it, and this lamination is generally done to prevent losses, core losses, or what we call it as eddy current losses. Okay, eddy current losses. These are core losses. Okay. Now, where we are now, we have drawn the yoke, right? And we have drawn the poles, right? Now the next one is a pole shoe. Pole shoe is nothing but it is just like to be more precise, so it is just like providing a more type a circular type of fashion, so that the field it will be completely linked with this conductor. Okay, because if you just keep it like this, then these areas, whatever the gaps are there, then there is a possibility that your flux will be leaking out. So that's why to overcome that one, to minimize that air gap, so to have a very good spread of your flux over this gap between your stator and rotor, you will be using this pole shoe. It will be just like in the form of a shoe. Okay, so this is pole shoe. It enlarges the region of the pole. Because of this region, flux can be spread out within the air gap, as well as extra flux can be passed through the airspace. Generally made up of your cast iron, any high magnetic material. The next one is a field winding. This is your field winding. Unless you flow any current through this one, you won't get any flux being developed there. The entire format of a pole shoe and pole core, they won't be working unless there is a field winding. Okay. Generally, this is made of a conducting material because it is supposed to follow the current. So, generally used is copper. Now, next comes the armature core. Now we have got yoke. Now we have got poles. Right. Now here comes your armature. This is your armature core and these are your slots. Okay. So this is your armature core. It includes a large number of slots across its periphery. And in these slots, armature conductor is with that. So this armature is basically, it provides a least resistance path for the magnetic fields, which means it will be having a very low reluctance. So generally we use iron type of materials, ferromagnetic materials, so that more amount of magnetic field is linked with the armature conductors. And this armature is also laminated in order to decrease the loss. Because see, this pole core, pole shoe and this armature all are made up of iron. And these are ferromagnetic materials. And the major thing is that they should link the magnetic flux which is developed by the field winding to the conductor. And here now comes the last one. We call it as an armature winding. Here in these slots, copper wire will be placed. Now this is act as a conductor. With this conductor, when it cuts a magnetic flux which is developed by the poles, then you will be experiencing an EMF. Okay. So armature winding refers to the copper wire wound across the armature, which is used as a conductor for development of EMF, which is required. Okay. Now this armature winding is turned with the help of prime mover, and it cuts a magnetic field and EMF gets induced. Generally, these are made of copper. Now all these windings now they should be brought out to some point, right? So these are brought out to the center. We call it as a commutator. And the main function of it is to collect the current from the armature conductors as well as supply the current to the load. So all these windings will be there, right? So all these conductors, they will be brought to your commutator and it will be provided to your load. And the biggest thing is that it provides unidirectional torque for DC motors. Generally, it is made up of copper because it is supposed to carry currents, and it will be made up of segments. See, if this is your commutator, it will be made up of segments, not a complete material. See, this is one segment. This is a material between this segment. This is mica, and this is copper. So alternately, mica will be placed between the copper segments, commutator segments. So this one is called as segment, commutator segments. Okay, and this will be connected to your shafts. So the current which is placed here, it will be collected with the help of brushes. There is another thing, we call it as brushes, generally made up of carbon. They will collect the currents from your commutator. So now you have seen that DC motors, how do they work? Now coming back to the construction, it is very simple. Operating principle also I told you. See, when the field winding, it develops a fields. On the stator, on the rotor, you will be having conductors. When the magnetic flux it is being cut by the conductor, EMF is produced. When EMF is provided a closed path, current starts flowing, so automatically there will be a secondary flux, thereby interaction of two fluxes, there will be a torque which is developed. Simple principle of DC machine. Now, based upon the field winding, connection between the field winding and the armature winding, DC motors are classified into two types. One is a self-excited. See, you are providing a DC supply to the fields. It is developing flux, right? Now this is being cut by the conductors, and again EMF is developed, and you are providing a DC, right? This EMF is developed, right? Now, whether you want to utilize the same one here or not. Now this is a big question. Separately excited and self-excited machines. Now the field winding is excited by a separate DC supply. Now both are not linked. This field is given separately and this is given separately. Then it is called as a separately excited DC motor. If both are linked, then it is called as self-excited machine. See here, the conductor also develops a flux, right? Armature flux. Now this is the same type of current. This is also the same type of current is flowing in both the windings. If both are linked, it is called a self-excited machine. The same excitation which are developing, it is being utilized here also. So based upon the connections between field winding and armature winding, they can be classified as self-excited. The first classification is separately excited and self-excited. In self-excited, you'll be having again three types. One is a shunt, the other one is a series, the other one is a compound. So this is the simple representation of a field winding. I'll show you. A field winding and an armature. Now here both are connected in parallel, right? This is called as a shunt machine. Now if you connect them in series, this is the representation. Not actually, this is not the connection diagram. This is the representation. This is a series motor representation, which means that both carry the same currents, the armature and the field. And if you do have both, it is called as compound machine. Now separately excited machine, this is a separately excited machine. Field is separate and armature is separate. Both are excited by the different things. Okay. So coming to the applications orientation. DC shunt motor, they are often considered as constant speed motors. Their speed doesn't vary much because of change in load. So that's why they are preferred as constant speed applications. So wherever, see, DC shunt motors, fairly constant speed and medium starting current. So these applications, fans, lathe machines, centrifugal, drilling machines, milling machines, machine tools. So drilling machines will be having battery operated things. So fans, battery operated fans, lathe machines, centrifugal machines, all these things you can employ DC shunt motors. But whereas if you want high starting torque and a variable speeds, then you will be going for DC series motors. Just like your high starting torque means a lift which you are supposed to overcome the gravitational pull at the time of starts. So a lift, elevator, hoist, cranes, locomotives. So for that things you will be using DC series motor. Otherwise you will be using DC shunt motors. These are exclusively used when you do have DC supply. Okay. When you do have AC supply, you will be using induction motors, isn't it? So for this, there is one more topic which I want to cover for you, an EMF which is induced in DC motor, that I will cover in the next video.